Neural networks have transformed natural language processing in ways that were once unimaginable. Traditional approaches to NLP relied heavily on rule-based systems or statistical models like naive Bayes and support vector machines, which could capture relationships between words but often struggled with understanding context, long-range dependencies, and the fluid nature of human language. Enter neural networks, powerful, flexible architectures that mimic the way the human brain processes information. But why are neural networks so well suited for NLP? The answer lies in their ability to recognize complex patterns, learn from vast amounts of data, and adapt to new contexts with remarkable accuracy. In this episode, we'll break down how neural networks are used in NLP, focusing on key architectures like recurrent neural networks, or RNNs, long short-term memory networks, LSTMs, and gated recurrent units, GRUs, and why they're particularly effective for sequential data like text. To understand why neural networks excel in NLP, we first need to recognize that text is sequential data. Each word's meaning often depends on the words that come before it. Unlike images, where all pixels are processed at once, text must be read in order, just like we do when reading a sentence. Early neural networks struggled with this because they treated input data as independent entities, meaning they couldn't retain memory of what came before. That's where recurrent neural networks, RNNs, come in. RNNs are designed to process sequences by maintaining a hidden state, which acts as a memory that carries information from previous words as the model reads through a sentence. For example, if we input the sentence, "I went to the restaurant and ordered a delicious," the RNN can retain context from earlier words to predict that the next word is likely to be something like meal or dish. This makes RNNs significantly more powerful than traditional models for tasks like machine translation, sentiment analysis, and text generation. However, RNNs aren't perfect. They struggle with a problem known as the vanishing gradient problem. As sequences get longer, the model has difficulty retaining information from earlier words because the gradients used for learning become too small, making it hard to update weights effectively. This means that while an RNN might understand short-term dependencies, it often forgets words that appeared much earlier in a sentence. To overcome this limitation, researchers developed long short-term memory networks, LSTMs, an improved version of RNNs that incorporate a gating mechanism to better manage long-range dependencies. LSTMs introduce three key components: the input gate, the forget gate, and the output gate. The forget gate is particularly crucial. It decides which information should be discarded and which should be kept, allowing the model to selectively remember important words while ignoring irrelevant ones. This is why LSTMs outperform standard RNNs in tasks that require understanding long sentences or even entire paragraphs. For example, in a text summarization task, an LSTM can retain key details from the beginning of a document while still considering new information as it reads further. Another improvement to RNNs came in the form of gated recurrent units, GRUs. GRUs are similar to LSTMs but have a simplified gating mechanism using only two gates instead of three: the update gate and the reset gate. The update gate decides how much past information should be carried forward, while the reset gate determines how much of the previous state should be forgotten. Because GRUs have fewer parameters than LSTMs, they train faster and require less computational power, making them a great alternative when working with large-scale NLP applications. While LSTMs tend to be slightly better at capturing long-term dependencies, GRUs are often preferred for their efficiency. One of the most exciting applications of these networks is sequence-to-sequence seq2 SEQ modeling, which forms the foundation of machine translation systems like Google Translate. seq2 SEQ models use two LSTMs or GRUs, one as an encoder to process the input text and convert it into a numerical representation, and another as a decoder to generate an output sentence in another language. This architecture allows for highly effective translations, summarization, and even text-based question answering. Despite these advances, both LSTMs and GRUs still have limitations. They process text sequentially, meaning they can't easily take advantage of modern hardware like GPUs, which are optimized for parallel processing. This makes training slow, especially for large datasets. Additionally, while they handle longer dependencies better than standard RNNs, they still struggle with extremely long documents or conversations that require deep contextual understanding. This is where transformers come in, a game-changing architecture that replaces recurrence with a self-attention mechanism. Unlike RNNs, which process words one at a time, transformers read the entire input sequence at once, allowing them to consider all words in a sentence simultaneously. This parallelization makes them incredibly fast and efficient. Transformers power models like BERT, bidirectional encoder representations from transformers, and GPT, generative pre-trained transformer, which have set new benchmarks in NLP tasks ranging from text completion to sentiment analysis. We'll dive deeper into transformers in later episodes, but for now, it's important to recognize that they were built upon the foundations laid by RNNs, LSTMs, and GRUs. So, what's the key takeaway here? Neural networks revolutionized NLP by introducing the ability to process sequential data intelligently. RNNs brought memory to language models, LSTMs solved the vanishing gradient problem, and GRUs streamlined the process with improved efficiency. While newer architectures like transformers have surpassed them in many tasks, LSTMs and GRUs are still widely used, particularly in applications where real-time processing or structured sequence learning is needed. These networks remain foundational to modern NLP, forming the bridge between early statistical models and today's cutting-edge deep learning approaches. As we move forward in this series, we'll explore how neural networks continue to evolve, diving deeper into transformers, attention mechanisms, and pre-trained models that push the boundaries of what's possible in NLP. But for now, understanding RNNs, LSTMs, and GRUs gives us a solid foundation for grasping how machines learn to process text sequentially, one step closer to machines that truly understand human language.